Greetings, Chem 110H, Dr. Bevilacqua here. I'd like to talk about heterogeneous equilibria. These are equilibria involving more than one phase. For example, a solid with a liquid, solid with a gas, or a liquid with a gas. I'm going to give you an example of dropping a piece of chalk or calcium carbonate into a beaker of water. And when we do that, we can ask the question, what happened? And the answer is, not much. But a little something happened. Some of the calcium carbonate went and dissolved as calcium ions and carbonate ions. And in fact, we can go ahead and depict that here with a little bit of calcium ions as 2+, but not too many, and a few carbonate ions, which are a little bit larger, as 2-. And so one of the important things to recognize is that while not much dissolved, the little bit of calcium carbonate that did dissolve ionized and made calcium ions and carbonate ions. We can go ahead and write down the equilibrium constant for this, obeying the law of mass action. And notice that we take the two products, calcium and carbonate, and write them in the numerator, raised to an exponent, that's the coefficient in the reaction, in this case 1. And then for the reactant state of calcium carbonate, we put that into the denominator, but instead of putting in the concentration, we put in the number 1, and that's by definition, although on the next slide I'll give you a feel for why we do that. But another definition is not only pure solids like calcium carbonate, but also pure liquids like water, or it could be a pure solvent, such as benzene. So we can then go ahead and write down an expression called the solubility product, or KSP, and that's written down for largely insoluble or sparingly soluble salts, and it's just the numerator in this expression. And the smaller the KSP is, then the less of the ions that are dissolved in solution. So on this slide, I pose a few questions. The first is, does more chalk dissolve if I grind it up? Well, at first blush, it seems like the answer to this might be yes. If there's a greater surface area, there will be a greater rate of dissolving. But it turns out that the answer is no. While there is a greater rate, a forward rate for dissolving, there's also a greater reverse rate for precipitation. And that's depicted here. Here's the large piece of chalk with a small rate of dissolving depicted by the small arrowhead and a small rate of precipitation. And here I've cartooned the ground up chalk with a big rate of dissolving, cartooned with the big arrowhead, but because there's a greater surface area, there's more surface to nucleate the precipitation on, and the rate of precipitation increases by the same amount. And because of that, KEQ itself does not change. Let's continue on, and if we ask the next question, what happens if I add another piece of chalk, such as I've depicted here in the right beaker, adding a second piece of chalk to the ground up chalk? Will KEQ change? Well, on the one hand, again, the forward rate, the rate of dissolving will increase, but so will the reverse rate. We've got greater surface area, and so will the rate of precipitation. And because of that, KEQ again does not change. Because KEQ does not change, whether we grind up the chalk or add more chalk, the reaction simply doesn't depend on the amount of solid or the way in which the solid is presented into the beaker. Because the reaction doesn't depend on the solid in any explicit way, we don't place the solid into the equilibrium constant, and by convention and convenience, we simply use the number 1. Thanks for listening.